Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6, and we're going to tackle two fundamental types of differential equations. Specifically, we will cover first-order linear differential equations and second-order non-homogeneous equations. The goal of this lesson is to understand the methods used to solve these equations and to confidently apply them to find both general and particular solutions. By the end of this video, you will be able to solve first-order linear equations using an integrating factor and solve second-order non-homogeneous equations by combining complementary and particular solutions. Let's learn together. We'll start with question 4.1. The question asks us to find the particular solution of the differential equation sine x times di over dx minus y times cosine x equals 2. Notice the term particular solution. This means our final answer will be a single function, not a family of functions. We'll find this by using the extra condition, y equals 3 when x equals pi over 4 at the end of our process. First, we need to identify the type of differential equation we're dealing with. This equation is a first-order linear differential equation. A first-order linear ODE can always be written in the standard form. d over dx plus a function of x times y equals another function of x. Our first task is to rearrange our given equation into this standard form. To do this, we need the coefficient of di over dx to be 1. We start with our equation. To make the coefficient of di dx 1, we divide every term in the equation by sine x. Now we can simplify using trigonometric identities. Remember that cosine x over sine x is cotangent x, and 1 over sine x is cosecant x. Applying these identities, our equation simplifies to di over dx minus cotangent x times y equals 2 cosecant x. Now this is in our standard form. From this standard form, we can identify p of x and q of x. Be very careful with the signs here. Comparing our equation to the standard form, we see that p of x is negative cotangent x and q of x is 2 cosecant x. This identification is a crucial first step. Making a mistake with the sign of pt is a common error, so always double-check it. We've now successfully converted the equation into the standard linear form, ready for the next step. The key to solving a first-order linear differential equation is to use something called an integrating factor. An integrating factor, let's call it r, is a special function we multiply our entire equation by. This multiplication turns the left side of the equation into the derivative of a single product. It essentially makes the equation easier to integrate. The formula for the integrating factor is r equals e raised to the power of the integral of p of x dx. As we found earlier, our p of x is negative cotangent x. So, our integrating factor will be e raised to the integral of negative cotangent x dx. Now we need to evaluate this integral. This is a standard integral you should know. The integral of cotangent x is the natural logarithm of the absolute value of sine x. So, the integral of negative cotangent x is negative ln sin x. Substituting this back into our formula, the integrating factor r is e to the power of negative ln of sine x. We can drop the absolute value bars here because x is pi over 4, where sine is positive. To simplify this expression, we use two logarithm rules. First, a number multiplying a logarithm can be written as the exponent of the argument inside the logarithm. So, negative ln of sine x becomes ln of sine x to the power of negative 1. This is our first crucial step to simplifying. Second, we use the rule that e and ln are inverse functions. This means e to the power of len of anything just equals that anything. Therefore, e to the power of len of sine x to the negative 1 simplifies to just sine x to the negative 1. Finally, sin x to the power of negative 1 is the same as 1 over sine x, which we know is cosecant x. So, our integrating factor r is cosecant x. Great job! We've found our integrating factor. Now that we have our integrating factor, we can proceed to the third step, the general solution. We use the general solution formula for linear first-order differential equations. The formula is r times y equals the integral of r times q of x dx plus a constant of integration, c. We've already found all the pieces for this formula. We have r equals cosecant x, and from step 1, q of x is 2 cosecant x. Substituting these into the formula, we get cosecant x times y equals the integral of cosecant x times 2 cosecant x dx plus c. Notice how we are meticulously substituting each part into the equation. Now let's simplify and solve the integral on the right-hand side. Cosecant x times 2. Cosecant x is 2 cosecant squared x. So we need to integrate 2 cosecant squared x. Again, this is a standard integral. The integral of cosecant squared x is negative cotangent x. Remember, the CO functions often have a negative sign in their integrals. Therefore, the integral of 2 cosecant squared x is negative 2 cotangent x. Our equation is now y cosecant x equals negative 2 cotangent x plus c. We have successfully solved the integral. This equation right here with the constant c is the general solution. It represents a family of curves that all satisfy our original differential equation. To find the specific curve we're looking for, we need to use the initial condition. We have the general solution. Now for the final step of finding the particular solution. The question provides the condition, y equals 3 when x equals pi over 4. We will substitute these values into our general solution. Plugging in y equals 3 and x equals pi over 4, we get 3 times cosecant of pi over 4 equals negative 2 times cotangent of pi over 4 plus c. Now we need to recall the values of these trigonometric functions at pi over 4. Remember the 45-degree or pi over 4 triangle. Cosecant is the reciprocal of sine, and sine of pi over 4 is 1 over root 2, so cosecant is root 2. Cotangent is the reciprocal of tangent, and tangent of pi over 4 is 1, so cotangent is also 1. Substituting these values into our equation, we get 3 times root 2 equals negative 2 times 1 plus c. This simplifies to 3 root 2 equals negative 2 plus c. Now, we just need to solve for c. We isolate c by adding 2 to both sides. So c equals 3 root 2 plus 2. Let's calculate its numerical value for the final answer. 3 times root 2 is approximately 42426. Adding 2 gives us 62426. Finally, we substitute this value of c back into our general solution to get the particular solution. Our final particular solution is y cosecant x equals negative 2 cotangent x plus 6.243, rounded to 3 decimal places. This is the unique solution that satisfies both the differential equation and the initial condition. Comparing our answer to the provided memo, we see that the steps and the final result match perfectly. This confirms our solution is correct. Now let's move on to question 4.2. This question asks for the general solution of the second-order non-homogeneous differential equation d squared y over dx squared minus 5 times di over dx plus 7y equals e to the power of x. This is a different kind of equation. It's second order because the highest derivative is the second derivative, and it's non-homogeneous because the right-hand side, e to the x, is not 0. It's also a linear equation with constant coefficients. The strategy for solving this type of equation is to find 2 parts of the solution and add them together. The general solution, y, is the sum of the complementary function, y sub c, and the particular integral, y sub p. We'll solve for each part separately. Let's begin with the complementary function, y sub c. To find y sub c, we solve the associated homogeneous equation. This is the original equation, but with the right-hand side set to 0. The homogeneous equation for our problem is d squared y over dx squared minus 5 times dy over dx plus 7y equals 0. This gives us the core behavior of our system. To solve this homogeneous equation, we form the characteristic equation. We replace each derivative with a power of a variable, which is usually m. The second derivative becomes m squared. The first derivative becomes m, and y becomes 1. So the characteristic equation is m squared minus 5m plus 7 equals 0. Now we need to find the roots of this quadratic equation. Since it doesn't look easy to factor, we'll use the quadratic formula. The quadratic formula is m equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. In our equation, a is 1, b is negative 5, and c is 7. Substituting these values, we get m equals negative 5 plus or minus the square root of negative 5 squared minus 4 times 1 times 7 all over 2 times 1. Let's simplify the expression under the square root, called the discriminant. Negative 5 squared is 25. 4 times 7 is 28. So the discriminant is 25 minus 28, which is negative 3. This tells us our roots will be complex. When the discriminant is negative, we express the square root of a negative number using the imaginary unit, j, where j squared equals negative 1. So the square root of negative 3 is j times the square root of 3. Our roots are m equals 5 plus or minus j times the square root of 3 all over 2. We can split this into a real and an imaginary part. M equals 5 over 2 plus or minus j times the square root of 3 over 2. So the roots are complex conjugates, a plus or minus j by v, where a is 5 over 2 and v is the square root of 3 over 2. For complex roots, there is a specific formula for the complementary function. The formula for the complementary function with complex roots is y sub c equals e to the alpha x times an arbitrary constant a times cosine of beta x plus another arbitrary constant b times sine of beta x. Substituting our values for alpha and beta, we get y sub c equals e to the power of 5 over 2x times a cosine of the square root of 3 over 2x plus b sine of the square root of 3 over 2s. We have now found the first part of our solution. This describes the system's natural behavior. Now let's find the second part of our solution, the particular integral y sub p. The particular integral is a solution that is just one specific function, with no arbitrary constants. Its form depends on the right-hand side of our original non-homogeneous equation. Our non-homogeneous equation is d squared y over dx squared, minus 5 times dy over d plus 7y equals e to the x. The right-hand side is q of x equals e to the x. When q of x is an exponential function of the form e to the kx, we try a particular solution of the same form. There's a special rule, but first let's see if we need it. The form we guess for y sub p is c times e to the x, where c is a constant we need to find. This works as long as the exponent k1 is not a root of the characteristic equation we found earlier. In our case, the exponent k is 1. Our roots were 5 over 2 plus or minus j times root 3 over 2. Clearly, 1 is not one of our roots. Therefore, our initial guess for the form of the particular integral is correct. No special rule is needed. So we will try the particular integral y sub p equals c times e to the x. To find c, we need to plug this guess, along with its derivatives, back into the original non-homogeneous equation. This will give us an equation we can solve for c. First, let's find the derivatives. If y sub p is ce to the x, then its first derivative, di over dx, is also ce to the x. And its second derivative, d squared y over dx squared, is also ce to the x. This is a very convenient property of the exponential function. Now we substitute these expressions back into our original equation. D squared y over dx squared minus 5di over dx plus 7y equals e to the x. We replace the y's and their derivatives with our guess. This gives us ce to the x minus 5 times ce to the x plus 7 times ce to the x all equals e to the x. This is the crucial step of substitution. Now let's simplify the left-hand side. We have 3 terms, all of which are multiples of ce to the x. Combining the coefficients, 1 minus 5 plus 7, we get 3. So the left-hand side simplifies to 3ce to the x. This means our equation is now 3ce to the x equals e to the x. For this equation to hold true for all x, the coefficients of e to the x on both sides must be equal. So we must have 3c equals 1. Solving for c, we find that c must be 1/3. And just like that, we have found the value of our constant. Therefore, our particular integral is y sub p equals 1/3 e to the x. This is the second and final piece of our solution. We have now completed the 2 main parts of our solution. Let's recap what we have. We found the complementary function, y sub c, and the particular integral, y sub p. The final step is to combine these 2 parts to form the complete general solution. Remember our formula, y equals y sub c plus y sub p. So we simply add the expression for y sub c and the expression for y sub p together. And that's it. This complete expression is the general solution to the second-order non-homogeneous differential equation. Let's write it down clearly one more time. The general solution y equals e to the power of 5 over 2x times the quantity. A cosine of square root 3 over 2x plus b sine of square root 3 over 2x plus 1 over 3e to the power of x. Notice the presence of the two arbitrary constants, a and b. This confirms it's a general solution for a second-order equation. For a particular solution, we would need two initial conditions to solve for a and b, just like we did in question 4.1. The memo provided confirms our answer. It shows the same complementary function and the same particular integral, resulting in the identical general solution. Our method was sound, and our calculations were correct. You have now seen the full process of solving a second-order linear non-homogeneous differential equation with constant coefficients. We've covered a lot today. Let's do a quick recap. In question 4.1, we solved a first-order linear differential equation. We achieved this by first putting it into standard form, then finding an integrating factor r to simplify the equation, and finally integrating to find the general solution. The condition y equals 3 at x equals pi over 4 allowed us to find the specific constant of integration and write the particular solution. In question 4.2, we solved a second-order linear non-homogeneous differential equation with constant coefficients. This required a two-part strategy. We found the general solution by adding the complementary function y sub c and the particular integral y sub p. Remember, the complementary function describes the natural oscillatory or decaying behavior of the system, while the particular integral describes its behavior in response to an external force or input, which in our case was e to the x. A common mistake to avoid in these problems is incorrect algebra or trigonometry. Always double-check your sign changes, logarithm rules, and integral calculations, especially when dealing with the integrating factor and the quadratic formula. Well done for staying focused and working through these challenging problems. You now have a solid foundation in solving these types of differential equations. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. We look forward to seeing you in our next video. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. See you next time.